walk you guys through the assignment on what I'm talking about, and it'll be a lot more explanatory. Explanatory things. I realized I didn't record. I had like a meeting that I had to go to. Oh, it was last minute stuff. So, yeah. Anyway. Because they were actually more stuff on my bag. Really? Yes. All right. And you guys ever work with JST connectors before? You know, there's like 7 different types. I'm like, JST connectors are the biggest pain in the butt. Not 7, not to the 7. Yeah. So I bought the JST. So I was looking them up. I was working on that stupid robot arm, and I got it to work with the power. I was able to reflash one of them and get it to work as it was supposed to, but they were all in parallel. All the servos were in parallel. Someone's not lucky. Someone else has lucky dogs. At any rate, so I got this. That was Thursday, and I rebuilt that arm, and I got everything working. I was able to reflash and recover the firmware on one of them. So the one that went to fun. I'm like, okay, that's good. Then I got them all able to move really good and like nice and solid. I'm like, right on. I'm like, but the connectors, like I could have cut the connectors and spliced in wires. I'm like, that looks just looks junky. So like, you know what? I know how to make cables. I'm going to make the cable. I'm just going to buy the cable, the wire, and buy this JST connector kit and crimper. Okay. So I ordered that Thursday. Friday, I was doing a couple of meetings and research, grading. So you guys' stuff was pretty much graded, but we have an exam today, which he's not here. Well, not you. He's supposed to take the exam. He's holding all of you guys up, but I want you guys to know that. But you're going to get it back Wednesday because he's supposed to take it today. So you guys look up that. Great exam, got all that stuff done. And Saturday the stuff came in, and I'm like, oh great, I'm gonna sit down and I had meetings all day Friday too. So half of you guys. I got the JST crimper. And have you guys ever tried to crimp JST connectors? It's not for the faint-hearted, especially when I can't see anymore. So I don't have my glasses. I got to buy a new pair of glasses. I'm not going to see, but I can't. Yeah, they're little, so I didn't get glasses. But my wife's been bugging me for the last, I don't know, year and a half, 2 years. Really needs glasses. Yeah. How do you drive? The cars are big. You can't read license plate. It's so wet. I'm not a cop. The biggest thing I noticed is when you're driving at night, right? That's when it gets, and there's absolutely nothing else on the road. So, anyways, I actually bought the connectors. Did I bother to plug in the connector to make sure it's the right one? No, because they're all just JST connectors, right? It's just JST. I get literally them all wired up, and I was happy with the wiring job. I even put some epoxy for strain relief on there and everything else about it. And I think my learning curve, I probably blew through a good 20 crimps and failed. The first 20, yeah. Second, that didn't work. Trying to come up with the process. I finally figured out a good process. I was consistently able to get a crimp. I thought, cool. So I get 3 of them done, so I'm now successful on 6 connectors. But I started to get the hang of it. I go to plug them in, and it doesn't fit. This doesn't work. Why is this not fitting? Oh, these are different. That's different than this one. Why is that different? It's JST. JST connector configurations. 7? You're kidding me. There's HX and there's EX and there's S and there's blah blah blah. Like, you got me kidding me. I was doing HX, not EX, which is what they were using. It was like, gee, I don't know. Needless to say, after wasting like 4.5, 5 hours of crimping wires, it was all for nothing. I even tried shaving them down and doing everything else. So finally, I just said, screw it. I'm buying the extension cables and calling them.
How many pins were there?
3.
Oh, well, they're tiny.
They're itty bitty little connectors.
Yeah, okay.
They're like I can do connectors. I've been doing connectors my entire life. I'm not a technician, but I'll still say I can do my work. And then, yeah, I know. So, it's kind of curious. You guys have never had JST connectors. JST connectors. All right. So I'm hoping we will do computer vision on Wednesday. We're going to go through the fundamental computer vision kernels. I'm actually going to do it in C#, just to give you guys a different view on how we can do things in C# and run some software that I've already written. I've done a lot of that computer vision, and so
Lecture lab.
lecture lab. This will be in the lab. You guys are welcome to join in. So we'll go through computer vision of how to do it, what are the kernel processes, how do we actually acquire information, what does color space look like, and why do we use it, all that kind of good stuff. We'll be doing on, I'm sorry, I'm just looking at the little control system. Okay.
They didn't do a good job of erasing the board.
What was your first thought? Okay, so let's do that. We'll do blue dot. Simulation 2. And Coppelia. Yay! Okay, so to do inverse kinematics, you guys want to go through the assignment first or go through this a little bit more detail first? This part? Okay, no, it's backward. Let's see. I'm not going to ask you guys.
Yeah, it's insane.
I know. Oh, by the way, when it says sparkling lemonade, don't shake it.
No, not that. Did you shake it? You should.
Oh my God, put lemonade in my iced tea. Great, oh, that's awesome. Sparkling, oh, it's going to have a little bit of bite. I shook it. It didn't get too much. Once I see it, open up, starts bubble up, I like quick stuck in the mouth. So let's look at this simulation. This is what you guys are going to be doing. Now, this should also come as no surprise. So what you're going to be doing, what you're going to be doing is using 1, 2, and 3. That should be and 3 no longer parentheses. And if. Never mind. Okay. What you're going to do is you're going to create a planar arm. That's my suggestion. If you guys want to create an arm in your group, but you can do the individual work, that's fine. But I really encourage you guys just to make your own arm. A planar arm that has to be at least 2 joints. If you want to do more than 2, that would be really good. I'm not saying your final is going to look like a 3-joint planar arm, but it might. It hadn't passed. Or any other arm you want. And I haven't written the final. I may say, you know, for the final we're going to do a little bit different. Maybe it's going to have one twist in it. Maybe not. I don't know. I haven't decided. I'm not going to kill you guys, that's for sure. So I'm going to kill you guys on the simulation assignment because you're going to have more time to do it. Bottom line. The simulation will actually be due the day of the last day of class. So you have until the end of the semester to do your simulation. So 20 months. There'll be more assignments, but that's when this will be due. And that reminds me, I forgot to give you guys bring the sheet that had the problems. Have you guys do chapter 5? We can do that real quick too. I can look at it. But what you're going to do is make an arm, and you're going to use the inverse kinematics engines like the one that I have here in the Armatron that I didn't post because I needed to make the change and explain to you what you need to do for it. You're going to attach a paint sprayer to the end effector, as the end effector. I'm going to show you guys how to attach that. That's the other thing why I didn't post it. You'll probably want to modify the default settings for the gun that you add. You can look at the version. We're going to look at this today so you can see what that means, what that looks like. I'm going to also want you to use graphs to indicate the position, velocity, and forces for the example as I show here. So this is why I want to go through the assignment so you can look at the Coppelia and ask questions about how did you do that? Or how did you do this? You're going to create the inverse kinematics script to be able to move it like you've seen me move it around with the dummies. You place the dummy at the base, dummy at the tip, and create that inverse kinematics script. You can choose, I don't really care, but you have to make a shape. Make the robot draw either a square, a 5-point star, or a hexagon. Basically something with straight lines. That's all I really care about. And it has to be a complete shape, more than three lines. You're going to change the trajectory for each one. So you're going to give it the velocities for the joints. Screen record that drawing the shape on the wall. And as the robot moves, it's going to show the Jacobians that are being calculated in real time in your video, okay, along with your graph. And in this case, you're going to discuss the relationships of the force of the graphs to the velocity and position, as well as the values observed in the Jacobian. Okay? So in other words, talk about the big picture from the simulation. Does that make sense? So if I go back over here, you can define the location of this dummy, and it'll follow the dummy. So you can change the position of that dummy if you want. And if we run it, let's go ahead and move this destination to the dummy. And you move it by clicking on this guy. We're going to move along just the X and Z. So you can make it draw something that looks right here. Okay. So it shows a square. And obviously you don't see that because it's trying to find its best location. Okay. So, my recommendation is don't make such a tiny robot. Make a little bit longer one. It just has to go in a square. Actually think, can you do that in a 2-degree of freedom robot? Here. I'll let you do a triangle too, but you might struggle getting to. You might probably strongly consider going towards a 3-degree of freedom robot arm. Okay, planar arm. You might be able to do it too. It might be real hard. So you can pick the poison on where your difficulty's at. Either a 2 or 3 degree of freedom versus the part I'm going to show you next. So that's part 1. Any questions so far? Just the overall approach to question 1. Question 2 is derive the Jacobian matrix expression. In other words, not the values. What CoppeliaSim gives you right here, as you recall, modules, kinematics, and we come over here to small. I don't know how it's shrunk. But we want to do actually tools. We want to do display IK world and Jacobians, and that's how you get the Jacobian right here. Okay. So that's the Jacobian matrix for 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6. So here is my velocities and each one of the joints because there's 5 joints. Okay. 1, 2, 3, 4, 5. That's why we have the 5 cross, where we have this 6. X, Y, Z, about X, about Y, about Z. That's what we see in the column. So you're going to calculate the expressions for this. Remember we did the partial derivatives and all that kind of stuff? You're going to do that. So you're going to come up with the expression for the Jacobian. But just like we did in the notes. Any questions on that? We basically did the 2 joint. You'll probably find it really hard to make the shape in a 2-joint robot. But a 3-joint is fine. You shouldn't have an issue on the 3 joints. Depending especially on how you do the next one. I'm not saying you can't, but it might be really difficult. Even if I give you the triangle, you might be able to do a square with 2 joints. Doesn't really matter. You can give it a shot. Your choice. But you're going to come up with the expressions for that Jacobian. So you're going to derive the Jacobian for the end effect. So you're going to look at the end of the tip, how it's moving across that seam. Make sense? Pick a joint set, whether it's in your reset state or whatever state you want to be in, So for one particular, you can drive the robot to a particular location, to a particular set of thetas, and watch to make sure as it's moving that the velocities agree with where it's going to go. So in other words, that this guy right here equals what it should for as it's going through. So this is going to be one that your Jacobian is in fact as it's moving that it's coming up with the right answer. Okay. Make sense? And you can pause the simulation as it's moving to see what the values are, as well as print out the velocities. So that's when you're looking at these graphs. That's why we want to see the velocities that we have right here. If you want to print it, like print the velocities, you can print the velocities for them as well. So here you can see the velocity right there. For a particular time, you can pause it and show that the Jacobian, for the angle that you set it to, or theta dot that it's set to, the rate you set it to, are in agreement. Okay. So basically, you're validating don't forget you're doing this in radians. So you're doing that derivation for that partial derivative for the Jacobian for that. Okay. So that's going to be part 2. And then part 3 is you're going to assign the velocities for the joints and use to find the end effector location. So this is validating the Jacobian, and then great, I got the Jacobian. Using this Jacobian here and the joint velocity space that you've defined to be right here, you can drive the different velocities. So the first one's going to be using IK to move it around. The second part, you're probably not going to really run the IK. You're probably going to do it in a coded mode. So you're going to not use the IK and the dummies. You're actually going to do, you're going to send the commanded velocities for each joint. Okay? You can compare and contrast the two of them because you can also print out the joint angle if you want. Actually, I'll take that back here. So where is my joint? Yeah, here's the joint angle right here. So you do have it right here. It's a little bit more tricky to use the inverse kinematics to drive it. Sometimes it'll be easier to drive it using using the set the velocity or set the target velocity or set the target position. So your choice to do that. So basically, you're using this, and you're going to have this velocity here in free space, not the joint velocity. So what is it? You can use the tip dummy right here. You can get his velocity and show what his velocity is, x, y, z, about x, y, z. And you really should. This guy really won't have your angular, because it's just going to be moving in the plane of x and y, or z to do that. Okay. So you guys have a month to do this. You guys have some time. Your exam might look a lot like this, just saying. It has in the past. So I'm elaborating the simulation to prepare you for the exam. Does that make sense?
Yeah.
There's more to the exam than that, but I'm asking you to do that. Much like the first simulation we did, if you remember. This is something to do on your own. And the reason why I say that is because it's going to help you prepare for the exam. I want you to be, it's a take-home exam, but I don't want you having to learn from scratch. I want you to take this month to really learn this material. Okay? Does this make sense so far? Okay. Which one file? Here. Okay. I will give you 5 points to your overall class grade if you do a 3 joints or higher. So you're at 87, you have a 92. Go from a B minus to an A. or an A minus to A minus.
And
B plus A
and the end
minus.
effector just has to move in a square?
Square, star, hexagon, or here. Your choice. So show that it does that in the inverse kinematics, and that inverse kinematics, and then do it in the forward kinematics. So you go back and forth between. So that's the idea right here. So you're going to do that. So you're going to create the script to do that for the inverse kinematics, and then you just do it for the inverse kinematics, drawing it around. But you're going to want to know what that is with the forward kinematics, so you can figure out for part 2 and 3. So if I were doing it, I use the inverse to find out where those points go to, so I can find out what those joints need to go to when I set that target velocity or that target position. But then we make sure that then we go and derive the Jacobian, and then we do that analytically or by hand and compare and contrast. And we use the velocities to get that end effector velocity. So we are doing chapter 5 in simulation, essentially.
And then we have to do it by hand, or
That's part 2, yeah. Well, I mean, yeah, you can do it by MATLAB, yeah. You don't have to, when I say hand calculate, I'm saying you're going to construct the expression. If you want to do the multiplications 100%, you can do it in MATLAB, that's fine, yeah. That's just a calculation. As opposed to, I know it's also a simulation tool, but we're using it as a calculation. 100%. If you want to do this in MATLAB, I haven't said you couldn't, but I have not lectured how to do it in MATLAB. You could do all this in MATLAB. They have the same features. I've never used it, and so I'm not sure exactly even how to do it. Could be done, I'm sure. I would say use Coppelia for the actually. I think, in my opinion, it's easy. My opinion is and then we do the velocities for that end effector. So we can print out on the graph. You can do another graph right here of just the end effector velocities, and not the degrees, not the joint velocity, but we can plot x, y, z, or vx, vy, and vz with the velocities that we see here. Yeah, this is all joint space. What is that end effector space, and how does that multiplication of the Jacobian work? Because that's really what we're talking about. Okay.
So, do you want us to include these graphs then?
Yeah, so I'm going to talk about how you construct those graphs. So that's why I was writing this up. I'm like, yeah, we need to walk through this. That's why I didn't post it. And we didn't get to it last week. Any questions on the assignment? I'm sure you will have questions as we go through the assignment. Do not wait till the last week to do this. We're done with chapter 5 now. Now's the time we start working. And now that you've learned it, I'll give you the homework problems to go with this as well. But this is really more important in my opinion.
Yeah. So you said this submission is going to be like simulation 1 with PowerPoint?
Yeah, and did you guys, I had a problem getting those grades to show up. Can you guys see them yet?
No.
All right. There were some new things I was trying with it, and I thought it worked, and I'm guessing it did. If those are not posted. Did you guys also want to do a quiz on chapter 5, where you have 3 attempts to do chapter 5 quiz? Just practice. Get you some free points.
Yeah.
So now that we're done, yeah.
One other question. You said this was due the last day of class.
This is the last day of class.
Okay.
So you guys have a month to do
So
this.
that's like
Okay.
Yeah.
Are we gonna get homework for chapter 5?
Yeah, I actually had written it all out, but I left out for that. So we can go back over, I'll open the homework, the book up, I'll get through this problem. We'll try to do this.
You're just gonna show us the Coppelia stuff on here right now, or? Because you said last day of class.
This is due the last day of class.
Oh.
No, we turn it in, you'll submit the zip files the last day of class. Yeah. We're gonna go through Lagrange relatively quick, and it's mostly background. We're gonna just flip through the slides and explain the slides when I call it a day. I'm not gonna test on it, I'm not gonna homework it at all. It's mostly informational.
So specifically about this Jacobian window in Coppelia, this is showing just the Jacobian matrix, or it's showing that and then also your joint velocity?
So I'm showing the joint velocity through the graph.
Okay.
So, and I'm talking about how you do that, because you don't know how to do that yet. We haven't talked about it yet. So I want to show you that, how you do the graphs. And you can also print them out like this as well. I need to see you after class one starts. Yeah. So you can print them out like I've done here, where you can see position, velocity, and torque. But I'm going to walk you through how I get all this information. And you're going to have to go a little bit further and get the velocity of the dummy as well. So you're going to go one step further. So I'm giving you a starting point. I'm giving you a good baseline, but I'm giving you the next step to do on your own. You may use any arm except for this one, obviously. And I wouldn't want to do the Jacobian on this one anyway.
So we can use one of those right there?
What's that?
Or do we have to build our own, or we can
No,
use those?
you can do any arm you want.
Oh,
And I
okay.
kind of would recommend making a simple planar arm. Yeah. I'm just telling you straight up.
Okay.
That's what I would do. I would do the 3-joint arm, take that extra credit, and get that much practice doing Jacobians. Maybe start with the 2, and then add the 3rd. You're really good that you can do that, you pretty much going to nail it final. Just saying. Okay, so any questions on the assignment before we go into the code on this particular thing? For this simulation. Okay, so one of the things you do is after you get done building the arm, you have, if you want to run the inverse kinematics tool that I showed you guys last time, I'll go ahead and stop the sim. You have to do a couple of things. I neglected to tell you guys this. David brought it to my attention. So I thank him for not, even though he's not here. You see this little dot? You have to have a little dot next to it. If you don't have a little dot, you will not be able to do the command script or the inverse kinematics tool. Okay. What do I mean by that? The little tools. So remember, you have the tools, and I think it's modules, and it was the inverse kinematics generator, right? So this is what you do, and when you use that, you put down the model, the base, the model, then the base of that, the tip. You'll notice there's all these different elements. You're going to put down the dummy tip, and it's going to be, there's a dummy tip somewhere here. I just can't see.
I think you need
Destination tip. No, that's not. It's called current tip. That's fine. Here it is. Down. You pick this guy as that guy here. The robot target. You pick the robot. Pick the joint group.
Like the target is the destination tip.
No, robot tip. Target tip, robot target, yes. So that would be to the destination tip, yeah. I want you to play around with the constraints. It may or may not be helpful, so you just play around with it. Usually I just leave it as is. 10 iterations should be fine. The damping factor. You remember when we were doing, we went through the inverse kinematics, had that damping factor, that's what it is. Go ahead and leave it at 0.1 for now. You shouldn't have to change it. And then you generate.
So we don't care about the joint group?
It's to leave empty if you're going to use all of them. Here's the thing: if this guy right here, if you click on this guy right here, click on the fundamental, come down to dynamic properties. No, wrong one.
Yeah, that one should not be a hand.
If we want to go to object, you have to say object is model. If you don't have that checked, you won't have the little dot. If you don't have the little dot, you won't do an IK script.
You turn the mesh into a
Model.
Okay.
In fact, you can export and save your arm if you want as well. If you go over here, so you can actually export this. So you can create a little thumbnail, and you can. These are all the different things you can do if it's These are the override properties. You can even give yourself a pat on the back and claim credit for it if you want. I don't care. But then you can actually export that model and save it. And just so you don't have to load it in, it's not just a scene, but it's a model. You can't do the IK unless it's a model. That's the one thing that I forgot to tell you guys. David reminded me, how come it's not there? I go, oh, there's not a little dot. How do you use a little dot? I forget. And he goes, it's this. That's exactly what it is. So, but I want to explain that more, and I also want to explain all the graphs. So that's why they just post the file by itself.
So like the way I did it was I used the floor. So I used like like you can use the floor.
You can use the floor as the base if you want to. Yeah, it doesn't really matter as long as if it's not a joint, it doesn't really matter. I go to that guy right here, the base. That's why I found it worked better. But it's basically a reference to the UCS. So we're going to go, if you're going to go to the floors, UCS, then that's what it's gonna reference out.
That means all my distances will be like really big.
Well, for the IK, it's not gonna matter, right?
Yeah, 'cause it's going to-
It's just trying to solve the IK. So it doesn't really, I would do it to the arm, but again, you can do whatever reference frame you want. Let's see. Anything on, I think that should cover that on there. So the next thing we gotta do is let's go ahead and look at the script itself. Notice that script right here. The destination tip is in that cluster with the Armatron base. So that Armatron base has the destination tip with it. It's trying to solve the IK within that space. So if you're going to pick the floor, then that has to be in the floor. So that's why I went to the base instead. This is a script that's going to generate, and I've significantly modified it because I wanted to include the graphs as well. The graphs, to do that, you right-click, we want to add, and we want to add a graph. That's how we add graphs. Okay, so here it has some graph. We want to rename that graph. So when we come down here, we need to name it what we're going to use. I put the graphs under the Armatron base as well, just to keep things nice and tight. I would recommend you guys do the same.
So you right click to customizable table? Is that?
No, I just right click the scene
Okay.
where it says right click add, and then I add a graph. But when you start up, notice it's just under the scene, so you want to drag it underneath that guy there. Where do you go? I thought I just created a graph right here. Wrong. Anyways. So you're going to create the graph and put it underneath. Again, we want to rename it. So again, it's going to have a handle. This is the handle you use to reference.
How do you make it?
So right click, add graph. Then you want to drag it into
Armatron base?
Yeah, you're thinking it's,
Okay.
oh, there it is, and then rename it whatever you want. So this is motor velocity, motor torque, motor position. Like you may want to have end effector velocity. Maybe you want to also have one as end effector position. So you can have multiple graphs. Okay. Yeah. So anyways, label whatever you want. And also, don't forget, whenever you make a change in the name, you have to hit the return. Otherwise, it ignores. You guys probably realize that. You don't want to do it that way. Let's see what else. You can go ahead, if you double click the graphs, you can do, if you want to have it visible when running, not running, show the time plot. You're probably not going to do X versus Y, so you don't have to worry about that. You can pick the frequencies, so how often you want that updated and what you want to say. Okay, so how do we get those graphs to do what we want? And by the way, thank God, if you're running a version of this from a couple of years ago, they got rid of the graphs. It was really awkward to make them. They put them back in to make it easy. So thank you for coding. All right, so let's look at the code. The code that we see right here is what was generated from the inverse kinematic script that was generated for it. But then I went ahead and added it. So this is default stuck in there. This is stuck in there. I put all of these in. Okay, so that's our speed point. I'm pretty sure they didn't stick that in there. Then I went ahead and I created these joints. And I went ahead and created this. This is the tip that the target needs. I've modified it so much I forget even what it has in there. So, but I will now post this scene for you guys. so you can then play with it. But I want to walk through it in more detail. This gets automatically generated. This is automatically generated right here for you. Some target, some tip, and some base. This tip position, I can't remember if that gets automatically created for it or not. I don't think it does. I think I added that. And then you have, I set this right here. This is automatically generated. This is automatically generated. This is automatically generated. And all of this is automatically generated. So the heavy lifting is done for you to a large point. Any questions so far? To do the graphs, what we need to do is create the handles or get the handles from the graphs. I just called it graph 1, 2, and 3 for obvious reasons. I then created these things called streams. So the streams are what gets put into the graphs. So the graph is going to graph a string. So what's the stream going to come from? So we're going to add a graph string. This is the associated graph. And then this is the label, the units for the label. Let's see, this guy here. And then this is our color. Right here. So this is the color of the graph itself. Again, if you want to look up the data, how to do it, go back over here and CoppeliaSim and sim.add graph. And there is this guy right here. Oh, that's right. It's the options is that one that we have right here, and that's just whether or not it's going to be visible. So, I just. So yeah, this little tuple for color. This is the option. This is the units, the name, and the graphic goes to. So I created the streams for velocity, torque, and position for each one of the joints. If you want to create another one for the other graph, you would add in whatever you want to call it, and then this adds it to the graph. Okay. So that's kind of the setup. Good so far? After that, we have the actuation. This gets handled for you. This is handled for you. In the sensing is where we're going to actually measure the values. So we're going to measure the velocity. So we want to measure the velocity of joint 1, joint 2, 3, 4, 5. Again, we're going to convert it to degrees per second. It comes in as radians per second. The force is going to come in Newton meters. We can get the joint force. Why am I having you do joint force? Because I'm going to have you guys do another assignment with this as you're going to do it. So I'm going to add something onto it, but it's going to be a little bit more. But I didn't want to have it as the same assignment unless you guys want me to do the same assignment. You guys tell me. Because this is chapter 5, basically. I was going to do another one where you're going to do the same approach but with chapter 6, but you're going to be using the force for the drawings. It's going to be an observation. So, if you guys want that in the same assignment, I didn't want to overload this assignment too much. Separate. He said separate. You guys all agree? And I'll do a third one, slightly different with the chapter following after the launch. All of them will be due at the end of the semester. So my suggestion is start on this sooner than later so that you get this kind of out of the way. You can build on the other ones. So what we're going to do is just get the values from that velocity. We're going to get the torques from each one of those joints, and we're going to get the positions from each one of those. Because this is a joint position, it's only going to give us a singular value. If I'm asking for pose, I'm going to get the quaternion. If I want to get the position, I'll get the x, y, z. If I want to ask for the velocity of it, not the joint velocity, but the position velocity, just the velocity, I will get Cartesian space. So this is all in joint space. Now that we understand joint space a little bit more, I hope that makes sense. Does this make sense? Yes? No? We're good? Okay. You can print whatever you want. That I just did. And then this is where we plot the graphs. So what we do is we're going to set the value, the graph handle, the stream handle, and the value. Pretty straightforward. Once you get the hang of it, it goes pretty easy. Copy and paste, call it a day. All this other stuff was built in by the script generator. You don't have to worry about it. And it's fun to read, but it's not required. Any questions on this? So you understand what's going on here. You understand what's going on here. You'll see this moving in the velocities. And so we're really decomposing chapter 5 into the details of what we talked about. I think chapter 5 is more important really than chapter 2. And I'm going to call it chapter 2, 2+, because and they kind of go hand in hand. Chapter 6, the Lagrange, once you go through that and you'll see it, it's almost apple pie and motherhood. You just do it. You just turn the crank. It's nothing so crazy about it. Chapter 7 is fun. It's not hard. It's kind of like you've already done it before. You've done it in physics. You've done it a million times over again. All we kind of just do is show how we're applying motion profiles and why we apply the motion profiles. To get to those motion profile discussions adequately, that's why we're going to Lagrange. But Lagrange, as you see it, it's really turn the crank kind of topic. And so once you turn the crank and let's let it do its thing, let it do its thing. Any questions on Coppelia?
Could we look again at when you're assigning the velocity graph in
Absolutely.
code?
Yes. I'll just close that down. Right here. So I'm assigning it to graph 1. So that's the graph I created. You talking about the declaration, or are you talking about the actual applying the value?
The declaration.
Okay, so this is our declaration. So create the object from the handle. So that has to agree. That name right there has to agree with this handle right there. Okay. Just like the objects before, the objects from the scene have to agree with the handle to create the object in this set. If you want to do this in Python, you can. I think Lua is actually more straightforward. Is it a major language? No, it's basically pseudocode. It doesn't require the spacing that Python gets complains about. So that's why we're doing this in Lua. If you can do Python, you can do Lua. So yeah, create the graph object and associate the handle from the scene. Create the streams that are associated. So think of these are objects in the object, right? These are data types within that object. You do it for each one of those, and then to simply generate in the sensing module, to generate the graph itself as it's working, we're going to get the values from the sim, and then we put those values on the graph. Okay. So it's really that simple. It does decompose values, but I didn't want to leave it hanging because I want you guys to use the graphs. And then again, my recommendation, it's not bad to do this. You can do the fixed widths if you want. White. You can do it there's ways of doing that in Lua. So if you look up Lua and how to do a print with fixed widths, you can do it. I've done it in the past. It's up to you if you want to. So just heads up on that one as well. Clear as mud or clear as water? Somewhere in the middle. Again, when I'm going to give you this scheme. Before I did that, I wanted to walk you guys through it. So if there's any things we need to have more clarity on, I'll update the files as necessary. But I think it's pretty straightforward. I'm a bad opinion. Any questions on the scene that you'll be doing? So I'm going to give you this scene. I'm going to give you the table, and I'm going to give you the wall. And you can put the table wherever you want to in the scene. So this is your wall you're going to graffiti. And then you can play with the person. Oh, I know what I forgot to do. The end effector. So that end effector has this paint sprayer sticking up. So to do that, we're going to come over into add. And we are going to do, let's see, I take that back. It's not under there. It is under, I don't remember where it's at. Modifiers. And here is our paint gun right here. If you want to use a welding torch, that's fine. I don't have a problem with it. It's kind of cool. This kind of goes away. You can change the persistences. Well, you literally just grab it and you drag it over and you attach it to the bottom, like you've done before you attach it over here. So here's the paint nozzle. And you can play games. This is actually the script for the paint nozzle. That's what comes built into it. You can goof around with it if you want. I mean, there's really nothing there to it. You can change the size of the nozzle. You can do these other properties here. You can do the color. You can do a whole bunch of other things to it. Keep it on explicit handling and keep it on show volume. So I think those are the defaults. Under the object, kind of keep the camera visible, and you can keep these general properties as there's no reason to change them. Those should all be defaults. But if you want to do the welding torch, that's fine too. It's your choice on that one. It doesn't matter. Basically, we just want to see this stay. You can change the persistence, which is how long it stays on the screen, to shorter or longer. I have it just set to pretty quick to disappear. Make sense on that? So again, put the end effector, or put that. You're going to have to probably rotate it. I think that comes up probably pointing up, so you're going to have to rotate it and do the silliness with that wonderful editing tool that Coppelia really has.
That one, those the figures already, or like the shapes, or no?
What's that?
Does that one, those the shapes, like paints the shapes, or no?
What do you mean?
Like if you run it, is it gonna paint something?
Oh no, I don't have this one painted. It's just going to be pure IK. So my suggestion is you're going to do the IK with this and make that shape. But here's what I would recommend. You know those joint angles. You know exactly what joint you need to make it go to get to that position. So you're going to draw it for you. It's going to tell you. You don't have to sit there and go, like, remember the first one you had to figure out where it needed to go? You're not doing that this time. You say, I want you to go so that my stars or my triangle is going to go down to here. So you can move the dummy to move it down here. You can even move the dummy off if you want to move it over here to the wall and move it along the wall if you want. You play games with the IK. That's going to give you the position of that joint set of angles. So that when you have to go in FK, you can do the FK. And you can also measure the rate of what those are looking like as well. So the IK is going to give you a lot of stuff up front. That when you then do the FK on your own, and you do the 4 reads and doing everything, then you'll know what those numbers are ahead of time. Instead of just goofing around going, gee, what should it go to? Or solving the IK. You don't know what the IK is. And the IK, to do the IK with those many joints, it could be done, but as you saw, the IK is usually done with the Jacobian. So I'm giving you guys a heads up. Solving that a little bit, making that solution a little bit easier to solve. But I still want you guys to practice doing the Jacobian expression. Last year I did, I'll tell you guys, last year's exam was a 3-jointed planar robot arm. Maybe I'll do a 4 for the next time. Once you can do them, you can do them. That's the point I'm getting at. Start with a 2 and then extend to a 3. But I'm telling you what last year's exam question was. I might have asked for a 3rd, but maybe I'll add a twist to it. Just to give it a twist, right? Give it a 90-degree twist. Maybe. I don't know. Maybe not.
Quite literally.
Literally. Probably I won't. But I'm not making you do a 3-jointed arm either. If I were doing it, I would do a 2 and then do the 3. Practice with the 2, because we already derived the expressions of the Jacobians for the 2. You do all the stuff and you go, okay, I got it down, and just drop it in place, you almost copy and paste into the 3, and you validate. Okay. And if you do that, you get 5 points of extra credit to your overall grade. My objective is for you guys to learn. My objective is not to punish you guys. There'll be a few more extra credits so that if you don't like your exam score, you can change it. But 5 points is pretty good. Probably too generous, but I'll give you guys more extra credits on the next couple simulation assignments. Any questions on the simulation assignments? Fun, easy, excited? You say no way. The other cool things, I know a lot of you guys want to go into robotics and autonomous systems for a job. Not all of you, but many of you. These are the kinds of things you talk about in your interviews. That you do know what the Jacobian is, that you do know how to solve it, that you understand what all of it is. I mean, you could get to a robot where it's already done for you, but you understand how that all works, and you understand the math, you understand all the theory that goes into it. That's really what you're showcasing. I said one of our guys, Jason, he's working for Haas. They make robots. Now, you can call them CNCs, but they're robots. Okay. And all the questions that we had from here, he was able to say, yeah, bang, 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 bang. And they said, okay, here's your job. Talked about the arm that they built. Here's the job. Done. Really? So, this is something you guys want to go in and do. And so, we didn't go to the controls. We could have done controls in detail, but the problem is half of you guys haven't had sufficient background in controls to go through the MIMO controller development. But you can appreciate that, especially in a grad school program. When we're doing the robotics, I guarantee you I'm going to have that as a class. Advanced control theory for MIMOs for autonomous vehicles and mini programs. Nobody has that in any program right now. I already know that. So we are working on, in fact, this Thursday we have a meeting to kick off the instructions of what we're going to be doing for the master's. Does that make sense to everyone? Everyone excited about that master's program? Who wants to come back and take the class? I might take years. I might make advanced robotics for autonomous vehicles for grad school. When you guys are thinking about grad school, what do you think? Yeah. Here's my recommendation. Go to grad school. Really? Go for a doctorate? No. That's up to you. That's a very personal decision. Very, very.
What made you want to go to doctor?
I want to be called doctor. It's an ego boost. It's not a bad, actually, that's not the reason, but it is a nice perk. I'm just going to say. I don't know. I've always been curious. I've always been doing all this stuff. And I figured if I'm going to do it, I might as well get a degree. So I was doing it anyway. So I might as well get something out of it, get a title out of it. It does command more money, but it can limit your job opportunities. So I'm just going to tell you guys that. Unless you want to be a professor. They might think you're overqualified and they want to pay you what you're worth. But they also may hire you in to do all really hard stuff. Really, really hard stuff. Fun stuff. Yeah, exactly. The fun stuff. Being a professor is not bad. It's a pay cut, but it has stability and the hours are less and you can do consulting. So everything has its advantages and disadvantages. Okay, we'll talk about the other stuff later. Any questions on the simulation?
Could we just do a quick scroll through?
Yeah. So these are all going to be posted for you.
Yeah.
That's really all there is. So it's really not that much. You guys will have a little bit more because you may be printing out the Cartesian elements and or graphing with Cartesian elements. both position and velocity. Torque doesn't make a lot of sense.
Question.
Yeah.
Is there a way to like output the data from this to MATLAB? So you need the API?
It's a good question. I've never tried it. I mean, I suppose you can just print it, capture it. You can probably save a file as a CSV.
Oh, okay.
You can do that. Yeah, I've never done file operations in Lua, but it can't be that hard. I'm sure you can Google it. You can give the answer pretty easy. Shouldn't be too difficult. I know the API does have save and open files. I don't know if it has it built into it or if you just run Lua. But I'll just do a CSV.
I just feel like graphs are easier to do in MATLAB.
Yeah, but it's not. Oh, you mean to do it real time?
Not real time. Just capture all the data and then process the data.
The problem is that you don't know what your simulation is going to do. I probably wouldn't do it that way.
No.
As I'm sitting there playing with the target,
I mean, like programming to the target and where to go into that square.
So here, let me just show you what I'm talking about. So if I wanted to draw and make this guy go over sideways, right? So I'm going to move him sideways. Let's get this a little better position.
You're not correct.
No, I have to do a couple of things. I don't need a torch. I'm just going to close that. Mouse position. So obviously I'm fully extended, right? So you have to kind of come down further. And if you just want to move along X, let's just really constrain it. But by the way, I don't care if the orientation is rotated 45 degrees. It doesn't have to be horizontal, it just has to be straight. So whatever it's going to take to make that straight line, notice the position that we're ending at. That's all. When it gets there, that's the position you would command those velocities to follow that path. Or not the velocities, to do the, this right here. The velocities, they're pretty much constant. Unless I go back and forth. But if you notice in here, right, they're pretty constant. They don't go up and down. They'll just say set the velocity and be done until you get there. So there's no acceleration. There's no acceleration profile. There's no jerk profile. There's no fourth, fifth, or sixth order profile. It's just saying the velocities and done. So it's simple. It's pretty simple from that perspective. There will be the extension of this where we will play games with the velocities. And we'll look at how the torques are adjusted. So the next assignment is actually going to have both Lagrange and velocity and the motion profile integrated into this assignment. There's a part 1 and a part 2. Does that make sense? Does that answer your question on why you probably don't want to do MATLAB? You just want to see what the position is like. Now, that position tells you exactly what it is. You can also, if you don't want to use the graph, I mean, it tells you right here, you just pause it. It says that that's what this joint 1 should be at. This guy here, joint 2 is here, joint 3, joint 4, and joint 5. Any other questions? Okay. So let's go into, we got about 15 minutes left. I knew today would mostly be about going up through the simulation. This is why I didn't know there'd be questions about it. That's why I didn't really post it yet. I will now post the file. So now you guys don't go in blind. Is that fair? And you guys, the due date's going to be the end of the semester, so you guys have a month to work on this. So it's not like it's due tomorrow, it's due next week. I want you to take your time. I want you to think about as it's working. Don't feel quite so rushed. And again, this is where that learning is really being internalized, so that when you take the exam's easy. That's my objective. If you all get A's at the end of the semester for this class, I don't have a problem doing that. I can justify it. Say, here's the work, here's the grade. Doesn't always work out that way. Average for this class is probably around an 83. You all probably thought it was more like a 63, but no, it's actually an 83. But if you want a higher one, I rarely see C's, and the reason it's 83 is just because there's like a lot of 80s. I've had an 85 average for this class. That's a lot of A's and B's. Are you working for it? Yes, you are. But go in that interview, if you want to do anything that looks like this, it'll help you a lot. The other thing you talk about is the fact that you're dealing so many different attributes of you're doing some the positions. This is not easy. This is not easy. It applies in so many other areas at the same time. The one thing I don't think it applies to is for so many MSETs, the HVAC, it doesn't apply to that. Can't stop. Unless you're going to do a robotic HVAC system. All right. We're good on all this? Simulation. I'm going to ask if I want to stay here or I'm going to stay here. Some people have said this is probably the hardest robotics class in college. They might be right. I just want to give you your money's worth. Spring 26. Oh, we are actually no longer. It's this one here. What I think I have to ask you as a question is, would you rather take an easy class and not learn anything? Or would you rather learn something? All right, so let's just pick the biggest file. That's motor theory. Was it really motor theory? That didn't love me that. It really wasn't motor theory.
Back up to this side.
Yeah, I would have missed that. Well, I'm just looking at file size. File size is probably good. And the most recent. So let's go to this one. Intro and background. This would be the file set. Did this get posted? Did I post this for you?
No.
Let me post it for you guys. Or if we just go through it real quick and then I'll post it. How's that sound? Or we have 10 minutes. This is what happened last time. We got 10 minutes left and we tried to do it, didn't we? Now I can do the lunch today.
Okay.
Yay! So let's talk about, so there's no questions on the sims, right? How about, I know what we'll do. Let's do this let me give you the homework assignment. How does that sound?
Yeah, because I still very
Chapter 5.
rusty in the coding.
So let's
I
go
need
through chapter 5. I have to pull the book up. Do I have the book in this directory? No. Online. Okay, which problem should we do? There's not too many on there. I'll post this in the computer. Question 1. 2, 3, 5, 6, 8, 7 is a really good problem potentially for an exam.
Are you gonna like put this on an announcement on Canvas or?
I'm just thinking, but without that goofy angle. So instead of having 3 planar, we could do 3 with a prismatic. So planar, rotational, prismatic. So that's a really good one to do. I haven't decided yet. The last exam I gave you was 3. And by the way, on the robot arm, I'm not stipulating they all have to be revolute joints. It just has to be 3 degrees of freedom. Now, clearly, you can't draw on the wall as shown in a Cartesian. So a Cartesian robot will not work. You have to have revolute. I didn't write that in there. But you have to have at least one revolute and at least 1 prismatic. You can't draw the shapes though if you only have that. But if you want to do 2 revolutes and 1 prismatic, or if you want to do 3 revolutes, I don't care. Fair enough? So 5.7, you're going to get the answer to, but I'm not going to assign it. Fair? So you have 2 joints, then 1 theta 2, and then the elongation. So I would encourage you guys to look at 5.7. So anyways, I gave you 5.8, right? I'd already gone through all of these. I can't remember what I did now. Nine. 10. 11. 13. Because 11 and 12 are almost the same. You can do 12 if you want. Again, these are things that I'm expecting you to know. That's really, this is telling you what I want you to get out of chapter 5. And I think maybe I gave you guys 13, right?
Yeah.
I mean, 14 is a slam dunk. 14. I mean, that's literally one line. D equals J times D theta, right? That's like done. So you may do MATLAB for all your calculations. Submit the MATLAB screenshots if you want. Do I need to write this down?
And 15.
Done.
And this will be turned in with example 5.12.
Yes. Yeah. So you have 512. I actually do it. You do on your own. So you have 512. And then if you can read back the problems.
Everything but 4, 5, and 12.
No, the back half I didn't finish.
1, 2, 3, 6, 7 is optional. 8, 9, 10, 11, 12, sorry, not 12, 13,
13, 16.
and 14.
And 16? No, did I get 16? No. Yeah, I guess that's what it was. That doesn't matter. You can always do more. No, don't get me wrong. So, like, if you look at this one, they're almost the same as this. They're all very similar. They're really just playing games with find the del operator, find del operator with respect to a frame, find D, find J, find D theta. That's all it is. That's all any of this is. The hard part is the J. Only one that asks you to derive the J is 7. That's optional. Why is it optional? Because I'm already asking you to do that for the assignment, for the simulation. Everything else is a very easy linear matrix. We've covered
So for the simulation, we don't have to derive like Jacobian. We already got it, right?
You have to find the expressions
Oh, the
for the
expression.
Jacobian. Remember you have the partial derivatives?
Uh-huh.
So you got to
Oh,
find the expression that does that. So that for any given theta, this is my number.
hmm.
So I want you guys to go through, yeah, that equals that one. I
Did we
don't want you to go crazy doing the Jacobians.
Did we do that in class? Like,
Well, we did the two joint in class.
okay.
Yeah.
That finding a Jacobian?
We found the Jacobian
Yeah.
in class on the two joint.
Okay.
The two joint
Resume
rotary.
to review. Uh-huh.
That's how we introduced it. There's two ways to find. We did a couple ways, right?
Okay, yeah.
In fact, there's several ways to do it. So,
And when do you want this by?
that's a good question. What day do you guys want? I'm flexible. How much time do you give me? Because there's no homework for the rush. And the other one, excuse me, is very easy. I mean, it's just motion profiles. It's something you guys didn't done in physics with a little bit of a twist. This is the heavy hitter. So you guys want to do 20th? No.
2 weeks from today.
That would be 1 week from today. We could do the 27th. That's getting close to, I mean, at that point, I could just say you turn it in when you turn in the last day of class. Yeah, we could do that. I don't have a problem with that. That gives you, well, that's 5 weeks away. No, I know you guys. Move to the calendar. Uh, 4/26, it's midnight. We'll do an electronic submission. What do you guys? So you can have the graphs. Or the MATLAB stuff and everything, you have to print out MATLAB. Sound clear? Fair with that? So if you do it with MATLAB, that's fine. Just say, here's the MATLAB, take a screenshot or do a copy paste, dump it in. You can use PowerPoint, Word doc, or OneNote. That's unfair?
Yes.
The objective of homework is to convince you, I'm going to give you the answers. So, I mean, the homeworks that I've graded, but you turn them in, I give you the answers. I'm not checking for correctness. I'm checking for completion. So homework is your tool to make sure you understand it. It's really saying, here's what I want you to know. That's all homework is. And for practice, then what you know, we'll put some problems. The simulation is confirming your understanding of what you know, both in theory and how you do the design. That's the objective of the simulation. So it's not just saying I know how to do the analytical or this type of stuff. I can just push numbers around because nobody cares. If you don't understand what those numbers are doing and how those are related to one another, it's irrelevant. So any engineering is like that. All right, are we good on that? 1, 2, 3. Somebody send me an email telling me what I wrote down. Or just take a picture. I'll take a picture. Are we good? All right, I'll see you Wednesday morning. That's the, you want to do a 9 o'clock start?
Yes.
All right, 9 o'clock start.